Hey guys, it's the final exam review. I am going to give people some time to hop in. If you guys have questions, you can drop them in the chat box. When you hop in, go ahead and say hi in the chat box. And we will give it a little while. I know some of you guys asked if Lily was coming, and she's around. Hey, Sharwan. But she's taking a nap in the other room, so I don't know if Lil's going to make it today. I heard her moving around, so we're just going to have to wait and see. Sorry, this desk is a little wobbly. I do apologize if it's glitchy and or, isn't the most tech savvy. But this is my home office, and I'm glad you guys are here today for a review. I've seen a couple of people send emails about questions, and I've added those into the slides or kind of in that way. So we'll give a few more minutes. Well, not a few more minutes, like another minute. And while I'm working on that, wait. I can hear my dog. I can hear her coming around the corner. We have hardwood floors, and she's bebopping around. So while that's happening, so Alexandria asks, is the Alex Pi due tomorrow or Wednesday? It is due the day of the final. So if your class, and I don't remember which class you're in, Alexandria, off the top of my head, if you have your final tomorrow, it's due tomorrow. If your final is on Wednesday, it is due on Wednesday. I have two sections, and they are due on different days because their finals are at different times. So I can, let me grab a pen, and I will email you, Alexandria, some clarification. So, the way I am going to work on this today, and hopefully this will all work as intended, I am going to use this template on my iPad and write. I'm going to do my absolute best not to write where the screen is. Ooh, Alexandra, it is due tomorrow at 3 o'clock. I will update Canvas accordingly. I'll take a look at it. So I'm so glad you guys came today. And so if you have other questions, you can drop them in the chat. Otherwise, we will look at this. So this is our first question. And so, I'll move it down. This is on the worksheet that I posted, but just in case you didn't download that, I'll go ahead and read it first. So a chemistry student needs to standardize a fresh solution of sodium hydroxide. He weighs out 1.28 grams of oxalic acid, which is H2C2O4, a diprotic acid, and it dissolves it in 225 mils of distilled water. The student titrates the oxalic acid solution with a sodium hydroxide solution. When the titration reaches the equivalence point, the student finds he has used 17.3 milliliters of sodium hydroxide. What is the concentration of this solution? So this is if you were to read the question and say, what is this? This is a titration. And so the first thing we need to do is acquire a balanced chemical equation. And so the balanced chemical equation in this case is going to be H2C2O4. And so we know it is a diprotic. And so if we use that information, these two hydrogens are our acidic protons. And on the exam, I would probably give you the counter ions. So it would say that there are two of them, and they are these. So we're going to add that to sodium hydroxide. And then we are going to create our product, which I will write underneath that so that it is not underneath my face. So in this case, we're going to make H2O plus sodium oxalate. So because these two hydrogens over here are acidic protons, we are going to get Na2C2O4. And when we do this, in order to have two sodiums on the right, we need two on the left. So there is a 2 here. And in order for this to be fully balanced, there is a 2 here. So once you have a balanced chemical equation, and I would always start with that, the first thing you want to do is you want to go ahead and look at you want to determine how many moles of your acid molecule you have. So in this case, we're going to take our 1.28 grams of H2C2O4. We're going to convert that to moles. So we're going to divide that by 90.04 grams in 1 mole. This is the molecular weight, which came from, and here it's going to be 2 times 1.01 plus 2 times 12.01 plus 4 times 16.00. Ooh, and Kirsten has a question as to why it is two sodium and the other. I'm going to move this down a little bit to give us a little bit more space, and then we'll move it right back. So if the oxalic molecule is H2C2O4, and it tells you that it's diprotic, which means there are 2 acid protons. So that is these 2. Which means when this dissolves to make an acid, you get 2H plus C2O4, 2 minus. And so this molecule here needs to be bound with sodium counterions in order to be neutral in the balanced equation. So if I had given you that H2C2O4 was composed of C2O4, 2 minus, you probably would have gotten there faster. And I would give you that if you had an unknown acid or base. I will tell you how it collapses. I think I used citric acid on the mini exam. It'll be just like that. Oh, I like the thumbs up. That helped a lot. So let's go back to where we're. Excellent. So from here, we can plug this into our calculator, and we're going to get that the student has 0.01422 moles of C2O4. And so from here, we now need to figure out how many moles of sodium hydroxide they have. So the question becomes, what do we need to do next? So you could determine the molarity and then determine the moles. But the 225 mils of distilled water is irrelevant for determining the concentration of the sodium hydroxide. So we're going to take our 0.01422 moles of H2C2O4 and use our balanced chemical equation, where for every 1 mole of oxalic acid, H2C2O4, we have 2 moles of NaOH, and that gives you 0.02844 moles. So I'm going to move this up just a little bit. Oops, not like that. So once we can determine the moles of, in this case, it's NaOH, now we can actually just figure out the concentration. And so in this case, we're going to divide by the volume. We're going to take our 0.2844 moles of NaOH and divide by the total volume, which in this case is 0.0173 liters. And hopefully when you plug that into your calculator, you get the same as me, which is 1.64 molar NaOH. Come back. Sorry for the flipping. Into the next slide. So as you guys look at this, if you have a question, you can drop it right in that chat box that I think is right about here. If you have no questions, then can you drop none in the chat and we will move on to the second question. So Sharwan asks, in reference to Hayden's statement that we had a triprotic acid once, would the acid have a charge of 3? Yes. So triprotic means that there are 2 protons. A triproton means that there are 3. So yes, it would have a charge of +3 if it was triprotic. So Kirsten asked, we didn't do anything with the 225. We do not need to use the 225 in this case. While that was there, if you had used it to determine the concentration in molarity of the oxalic acid, then you would have multiplied that by the same volume, and that would have given you the exact same value. For example, I'm going to move this slide over a little bit so I can, ooh, not like that, not like that. So if we had used the 225, we would have taken this number of moles. So we would have taken 0.01422 moles divided by the 0.225 liters. And I didn't set this up, so it'd be 0.1. That gives you a molarity of 0.0632 molar. And in order to use that in what I would consider a classic or a more typical titration question, we then would have had to take the molarity and determine the moles. So we would have taken our 0.0632 molar, multiply that by the volume, which is 0.225 liters. And that would have given us the number of moles that we had started with, which in this case was 0.01422 moles. So that 225 volume was not irrelevant, but not necessary for the calculation that we did today. It's a great question. Let me check my chat box. And it looks like we're good to go. So in that case, I'm going to go ahead and move forward to the next question. So this next question is in reference to chapter 10. And I forgot that this covers up part of the screen when we use it. So good enough. We're just going to leave that alone. So the question here is, how many moles of Lysol are contained within a 450 milliliter Lysol spray can if the can is stored in my office at 22.1 degrees Celsius and the pressure inside the can, not in my office, is 1.891 atmospheres. So this question is a PV equals nRT, and we just need to determine what the values are. So the pressure in this case is 1.891 atmospheres. The volume is 0.450 liters, because we can convert milliliters to liters, so 450 milliliters divided by 1,000 milliliters in 1 liter. N is what we're solving for. R, we are going to select in just 1 second. And the temperature here is 22.1 plus 273.1 0.15. And when you plug that in, I get 295.25 Kelvin. So from here, we can then solve for N, which is our value. And so N equals PV over RT. And so from here, we can just calculate that value. And so the pressure is 1.891 atmospheres multiplied by the volume of 0.450 liters divided by R. In this case, because of the units that you see in these values, I'm going to select 0.08206 liters, atmospheres, moles, Kelvin. So 0.08206 liters, atmospheres, mole, Kelvin, multiplied by the temperature, which is 295.25 Kelvin. When I plug this into my calculator, I get 0.0351 moles. And I double check my significant figures. And so the temperature here only has 3 sig figs. So we are going to continue to use that value in our answer that we see here. Ooh, it looks like someone asked about the Alex due date and it was answered in the comments. So if someone asks a question that you know the answer to, feel free to drop the answer in the comments. Does anyone have any questions about this example? And if you do, you can drop the question in the chat box. And if you don't, you can drop none or an emoji, whichever works. So Avery asked, the R value will be on the equation sheet for the exam. It is. And in the final exam module that opened on Friday, the equation sheets are in there. And you can check on that. So all of the R values and all of the equations from chapter 10 are on there, which are new. So we have the equations, we have the R values, and all of the pressure conversions are in there. So that will definitely be in there. I checked just again this morning to make sure. Excellent. It looks like we don't have any questions, which is good. There is a couple of chapter 10 examples. So Jeremy says that the sig figs, the answer should only have 2 sig figs, and the answer should have 3 sig figs. So in that case, there's 2 reasons that we did that. And what are they? So one is the temperature, which is 22.1. And so when you add 273.15, I kept that value. And so in that case, the sig figs moves to 295. I kept all of those digits, but that one actually has 4. So technically, I think this should actually have 1 more. So it should have 4 sig figs. And that answer is should be a 2 at the end of that. So Avery asks, what words in the problem are a hint that we should use PV equals an RT? So the hint that I would use is that it asks for the pressure and it provides several other values that you could have described into these type of questions. So because it gives you a pressure, a volume, and a temperature, it's usually a good indication that it's a PV equals nRT question. So the next question, I am going to read it and then I'm going to continue to slide up. So as you can watch how I write, some of the writing will proceed up the slide. This one is quite a long calculation, but it's everyone's favorite topic. So it reads, if 15.289 grams of aluminum hydroxide reacts with 17.293 grams of sulfuric acid and excess water to create aqueous aluminum sulfate and liquid water, how many grams of aluminum sulfate would be created in this reaction? How many grams of aluminum sulfate would be created in this reaction? How many grams of the excess reagent remain? If they only collect 12.403 grams, what is the percent yield? Hold tight, we're getting several burning questions about Sig Figs, so we'll switch back to that slide. So it should have 4. So I think when I did the calculation, I lost a Sig Fig here, which is the other reason that looks terrible. Oh God, it won't let me edit that. So this value here should have 4 Sig Figs as well. So the answer should have 4 Sig Figs. I think I know there's a delay between when your comments come in and when I see them. So if I answer your question twice or it's way out of sync, that's what's happening. So in this equation, what we need to do, or in this question, and so in this case, what the question is asking is, what is the limiting reactant? And so this is limiting reactants. So from here, we need to, all right, hold on. We're going back to the other one to answer some other questions. So the reason, let's see. So the question becomes, so why is it 4 if 22.1 has only 3 Sig Figs? So to calculate temperature, it's 22.1 plus 273.15. And that gives you 295.25. And that value should only have 4 Sig Figs. And so that converts to 295.3. I kept this, I can't see that. I kept the remainder of these for accuracy, but for in terms of Sig Figs, this value is where it comes from. So part of the question I think has to do with Sig Figs. So I'm going to wait just a second before I scroll up a little bit. So Sig Figs for multiplication / division, it is the least number of Sig Figs. And that's pretty simple. You just basically count them up. So is it 3? Is it 4? Is it 5? That's how many you can have in your final answer. For addition and subtraction, the reason these Sig Figs are more complicated is because they're controlled by the decimal point. And so it is the least number of decimals of, we'll say values after the decimal. So these are all great questions. I'm happy to answer them. So in our limiting reactants problem, the step number 1 is to determine a balanced chemical equation. So in this case, Oh, hello. So here we are going to determine our balanced chemical equation, which is 2 aluminum hydroxide plus 3H2SO4, and that gives us Al2SO4 3 plus 6H2O. And based on the equation, we should include our states, and so we have solid, solid, aqueous, liquid. And so if the states are not provided, you don't need to include them. If they are provided, you should as part of your value. So once we have a balanced equation, so this would be what I would call step 1. Step 2 is to identify the limiting reactant. And so we can do that by taking both of our starting materials, and I'm going to convert them to the other side. So I'm going to take I'm going to start with the 15.289 grams of aluminum hydroxide. And I'm going to convert that into sulfuric acid. So from here, aluminum hydroxide weighs 78.01 grams and 1 mole. Now I'm going to multiply that by 2 moles of AlOH3 plus 3 moles of H2SO4. Now we're going to multiply that by the molecular weight of sulfuric acid, which is 98.09 grams and 1 mole. When you plug all this into your calculator, you're going to get 28.85 grams of sulfuric acid. And so we have 17.293 grams. And so in this case, that tells us 2 things. Aluminum hydroxide is not the limiting reactant. There will be excess left over. So in this case, the question asks how many grams of aluminum sulfate would be created, how many grams of the excess remain, and about the percent yield. So in this case, in order to determine the excess, we need to know how much of the aluminum hydroxide will be used when the limiting reactant is consumed. So from here, I'm going to take my 17.293 grams of H2SO4 and convert that directly into aluminum hydroxide. And so the 98.09 grams and 1 mole of H2SO4, and there are 3 moles of H2SO4 for every 2 moles of aluminum hydroxide, and it's 78.01 grams and 1 mole. So when you plug that in your calculator, I get 9.1686, and no one can see that, so we'll make it a little bit bigger, grams. And so from here, we can determine the excess. So we are going to solve these slightly out of order. So the excess aluminum hydroxide is 15.289 grams minus the 9.1686 grams. And that gives you 6.1204, and that has too many sig figs because you can only have 3 after the decimal point. And so with sig figs, that is 6.120 grams of aluminum hydroxide remaining. So we've got a couple of good questions in the chat box. So Bertram asks, how do you know that it's aluminum, it's AlOH3, not just AlOH? So that is a good question. And I'm going to come back to the previous slide. Ooh, Mahi's taking that in the chat. And she is definitely correct. Aluminum has a 3+ charge, so Al 3+, and OH has a single negative charge, and so together you need to balance those charges. So for every aluminum, you need to have 3 OHs to make it neutral, so that gives you Al OH 3. Great question. So Catherine asked if the 28.85 is for sulfuric acid, and that is definitely true. And so in that case, I did update that in the text down below to where it says that. And so these values over here that are underneath that, so we'll box them over here. These are the amount required. So if you remember when we talked about limiting reactants, I talked a lot about making grilled cheese sandwiches. So this is how much you have to use all of your starting material. Great question. So from here, I am going to keep solving this, and then I will come back to answer Eric's question. So we now have the excess reagent. It also asks how much product is created. So I'm going to move this up because space. So from here, because the question asks how much is created, we can use the starting material that is the limiting reactant and convert that to product. So you could take your 17.293 grams of sulfuric acid. And from here, it is 98.09 grams in 1 mole of sulfuric acid. So there are 3 moles of H2SO4 for every 1 mole of the aluminum sulfate. And for every 1 mole of that, it is 342.17 grams. When you plug this in your calculator, you should get 20.107 grams of aluminum sulfate. So once you get that, sorry, I tried to turn off all the alerts on here. So once we have a total mass, so this is our expected yield, otherwise known as the theoretical, and it gives us it asks for us to calculate the percent yield. And so the percent yield is actual divided by theoretical, multiplied by 100. And so in this case, the actual yield came directly out of the problem, which is 12.403 grams divided by 20.107 grams times 100. And that gives me 61.685%. So Eric asks, what is the good way to get good at doing the mathy questions fast? Kirsten says practice. Mahi gave it the double arrow that says this. I concur. So the best way to do this is to continue to practice. I think that one of the things that will help with practice is looking at the problems and trying to identify what to do. So some practice options that you have. You can poke around on my YouTube channel and find other live videos where I've solved more problems. And you can basically read the problem, hit stop, and then try it. You can do the chapter worksheets if you've never done those. There are some questions in the back of the book that you can try if you have access to that. But practice is the way that you can do this. And so as we look at this limiting reactants problem, which was quite long, what questions do you have? And if you have none and you now wonder why limiting reactants were so hard in the past, you can drop none right in that chat box, and then we can work on the next problem. So, Eric, are you practicing with the calculator that you're going to use on exams? Because I find that if you're using a graphing calculator when you do your homework, then I think that might be part of the issue. So Skylar asked, H2SO4 is the limiting reactant, but because we have 15.3 essentially, and you need 28. Correct. So you need 28 grams in order to use all of the aluminum hydroxide. And so by having less of that, it makes it the limiting reactant. So that is exactly correct. So, got a lot going on in the chat, which I am so excited about. So, Alexandria asked, can we go over identifying the limiting reactant again? Yes, let's do that. So, I'm going to use colored pencil, colored iPad pencil, to try to give some clarification on how I did this calculation. So if we start with these two products, and that information comes out of the question. Oh, Alexandria said she answered her question already. Excellent. Okay. So Catherine asks, why did you use a conversion to get to the final 20.07? So there are two ways that you can set up a limiting reactant, and I have shown you the one that allows you to calculate the excess. The other way that you could do this was to take both of your starting materials and convert those to product. The one that makes the least product is the limiting reactant. And so that gives you this value. Both of the values up here, highlighted with the blue wiggles, are this basically gives you the information about how much of your limiting reactants you can have. And so both of those give you that information. And so you could have calculated from both blue boxes on the left side. You could have taken that information and then used those to determine product. And that would allow you to answer 2 of the questions that were asked. The other question that asked about the excess reagent, you would need to convert the limiting reactant to the other reactant in order to do that. Does that answer your question, Catherine? While you work on that, I'm going to go ahead and flip to the next slide so we can keep moving in the interest of not, I won't say I don't want to hang out all day, but it turns out, like in a non-shocking twist, I still have a final to write and things to do. So on this next question, so on the worksheet, it's titled number 4. It says, pure hydrogen gas is produced when zinc solid interacts with H2SO4, so sulfuric acid. What is the pressure of hydrogen gas produced when 21.34 grams of zinc is mixed with excess sulfuric acid at 31.4 degrees Celsius and is collected in a 312 milliliter balloon. So in this case, this question starts to look like some other things. So instead of saying, we know what this is, let's think about how we could figure that out. The first thing I would do is write down, what does the question tell you? So we have a balanced chemical equation, which is provided here. So in this case, we have everything we need in that case, which is good. We have a volume of 312 milliliters. It almost always has to go to liters, so we're going to go ahead and do that, of 0.312 liters. We have a temperature, which is 34.1 degrees Celsius. And so it asks us up here, what is the pressure of hydrogen produced in our sample? So from here, what we need to be able to do is to try to figure out what is the pressure. So P equals question mark. So the equation that we most often use with pressure is PV equals nRT. So we have the volume, the pressure is what we want, we have a temperature, our value can come from there. So the other part we need to figure out is the N. So in this case, it's going to combine material from chapter 3, where we use the balanced chemical equation, with PV equals nRT. So in this case, we have our 21.34 grams of zinc, but it asks about the pressure of hydrogen gas. So we need to convert grams of zinc into grams of hydrogen. So we're going to do that using balanced chemical equation. So the molar mass of zinc is 65.39 grams in 1 mole. And per the balanced chemical equation, it's a 1-to-1 ratio. So 1 mole of zinc is equal to 1 mole of hydrogen gas. And in chapter 3, we used to convert that all the way to grams, but we don't need to because we needed N is the number of moles. So this gives us 0.3623 moles. And this is our N value. So we need the pressure, and now we have everything else that we need. So in this case, we're going to set up a calculation where P equals nRT over V, and our 31.4 grams of Celsius plus 273.15 gives us 307.25 Kelvin, and I'm going to keep everything that's totally underneath my face. So I'm going to keep all the digits together so that we can have the most accurate answer. So the pressure here is our 0.3623 moles times the R value. I'm going to pick 0.08206 liters atmosphere. Because this is going to give me the value in the correct units, or in units that I like, multiply by 307.25 Kelvin. I'm going to divide that by the volume of 0.312 liters. So when you plug this into your calculator, you should get that 29.3 atmospheres equals the pressure. At least that's what I got. So in the chat, I can see that Kayla gave Eric some suggestions of trying to do it step by step in your calculator. And I fully concur with that method. I find it difficult to set up everything in my calculator. The other thing that I'll tell you is when I grade things, if all of your work is correct, but your answer is wrong, then you will earn partial credit for every part that is correct through the thing. So you can always make sure that your setup is correct, and then that will help you as well. So does anyone have any questions about this calculation of the pressure inside a tank where gas is collected off of this reaction? If you have no questions, you can drop none right in the chat, and then we can go from there. So Bertram asks, would it be okay while doing the equations if you don't include the units? You are never required to include units. The only problem is if your units don't make sense. I always recommend that you include units, but there is no, I will not take off points for no unit. I typically don't, for no units inside the calculation. So you're good without. But I would recommend that you do it, because if you mess up something, it's easier to follow that with the units. And other than that, it looks like there are no questions. So let's look at the next one. So this question is, what is the concentration? And it should say, what is the concentration in molar of a solution created when 35.182 grams of sucrose with a formula is dissolved in 500 milliliters of water. How many carbon atoms are in the solution? So from here, concentration in molar is moles divided by liters. And so we can convert our grams into moles and divide by the volume. So in this case, we're going to take our 35.182 grams of sucrose, which is C12H22O11. Then we're going to divide by the molar mass, which is 342.34 grams in 1 mole. And this is going to give you 0.10277 moles. So from here, I'm now going to do the concentration, which is the 0.10277 moles divided by 0.5 liters. And that gives you 0.20554 molar sucrose. So from here, that's part one of this. The second part asks, how many carbon atoms are in the solution? So concentration is chapter 4. Number of atoms is chapter 3. So for the atoms, I'm going to take the moles of 0.10277 moles of C12H22O11. And then it asks how many carbon atoms. So there are 2 ways you can set this up. I'm going to pick the one that works for me. You can pick the alternative. So for every 1 mole of C12H22O11, there are 12 moles of carbon. For every 1 mole of carbon, there are 6.022 times 10 to the 23rd carbon atoms. The main difference between the 2 methods is you can switch these 2 steps. There is no right or wrong answer when you do this. So when you plug this into your calculator, you should get 7.4266 times 10 to the 23rd atoms. What questions do we have about these 2 calculations that are fully separate? And while you're thinking on that, I think it might have been Eric. Someone asked long ago, and I did see it, Yeah, Eric Lawley asked, like 30 minutes ago, but I saw it. I just forgot about. He asked about the key for the midterm, and I thought that was up. So I'm going to make a note, and I will post that when we are done here. Not seeing any questions, but I'll give you guys a second to drop those into the chat box if you have one. It looks like we have no questions on this calculation. If you do, you can always drop it in the chat box and we can come back to it. All right. So in this next question, it says draw the electron configuration for rhodium and write the configuration for rhodium 3+. So in this case, the first thing that you're going to do is identify rhodium on the periodic table. And rhodium this is element 45. And it doesn't say that you can use the noble gas configuration, so I would assume you need to do the whole thing. So from here, it's important to follow along in your periodic table and make sure that you go through all of the different orbitals. So we have the 1s, the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and then the 4d. So don't forget that the d orbitals are slightly offset in comparison to the end shells as you go across. So from here, we want to add in our 45 electrons. And don't forget to use Hund's rule when you get to any of these. And Charwan asks, isn't it an exception? And it is an exception. So when we get here, we need to remember that rhodium is an exception. And so we are going to remember that rhodium just promotes a single electron out of the 5s. To give it, instead of 7, it will give us 8 electrons in the 4d orbital. So rhodium is an exception. And so the second part of this asks us to write the electron configuration for the rhodium 3+. And so in the interest of saving time, instead of writing all these things out, I'm going to use the noble gas configuration for this, but you would just write out, I'll write the whole thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Here's the other part. For a transition metal, all of the electrons from the s orbitals are lost, regardless of which one it is. So the 3 electrons that we're going to lose in this case are this one, and then 2 out of here. And so that's going to give us the 4d46. So Bella asks, how can you tell when it's an exception? So in this class, there are 2 ways that you can tell. For the last slide, it's not the last slide. one of the last slides in chapter 6 has a picture of the periodic table and has them circled in hot pink. So some of the exceptions, and not all of them, but some exceptions, it's like literally not what I asked it to do. So exceptions, some of them are chromium. Sorry, it keeps moving around. We're just having technical difficulties. Chromium, copper, molybdenum, ruthenium, rhodium, palladium, silver. So I think this is all, sorry. I think these are all of the exceptions that are in the D transition elements. So there are several transitions in the F block, but I find that those don't really participate in patterns. And so I will not ask you about exceptions that are not in the D elements. So those you can look at the graphic that's at the end of chapter 6. Other questions, if you have any other questions about the drawing or writing of the electron configuration, you can drop them right in the chat. If you don't have any, so Kirsten asks, how would we draw rhodium 3+? So for this one, I am going to use the noble gas configuration. So to draw the rhodium 3+, you would put krypton 1, 2, 3, 4, 5, 4D, and so there are 6 of those, and it would look like this. And so in this case, if you were to be asked to draw it, you can put the 5s. So if you wanted to, you could put it, well, that's not going to work. You could put in the 5s here. That's, you know what, we'll just redraw it. So you could draw it like that, leaving the 5s empty, or leave it there. All right. So Catherine asks, did you leave out 5s because it's only 1? So I left out the 5s in the exception because when you lose the 3 electrons, it loses, regardless of how many and whether or not it's an exception, it loses all of the s orbitals plus 3 more. So, or plus any additional electrons. So for a transition metal, when it becomes an ion, the electrons that are lost are the s electrons plus any whatever remains to be lost in the d orbitals. So that's why the 5s is left. And this is for RH 3+. So that's the answer to Catherine's questions. Avery asks, are you going to ask noble gas configuration on the final? Both of which are valid. Make sure that you read the directions because it will either say you can use this or you cannot use this. And if it doesn't specify, you may do it either way that you like, as long as you answer the question. And Alexandria asked, can you go over how to draw out the exceptions? Sure thing. I'm going to move this up to give us a little bit more blank space. So for an exception, so we will look at chromium first. So I'm going to, so for chromium, And it would look very similar for molybdenum. So for chromium, it has the 4s and the 3d electrons. So in this case, so chromium has 24 valence electrons, 18 of which are in the noble gas, so that's argon. And so from here, we've used 18, so there are 6 left. So the reason that it's an exception is because we could get this. So this is 6 electrons, but the exception says that this electron is going to be promoted here to where you get this. So you get 6 equivalently filled orbitals. So that is the half-filled orbital exception. The other exception is for things like copper. And so copper is also argon. And we have the 4s and the 3d. And so there are 10 electrons, 11 electrons. So copper would look like this without the exception. And so from there, we're going to promote this one here to give you 4s and it has a fully filled d orbital because this is lower in energy than leaving a fully filled s orbital and moving forward. So the exceptions are just about whether or not it can and does remove electrons from the s orbitals and move them into the d orbitals. Great questions. I don't see any other questions in the chat box, which tells me that you guys are doing great. Does anyone have any other questions? If you don't, drop your favorite emoji in the chat box or you can just drop the word none. And then we will move on to number 7. Sweet. It doesn't look like there are any questions. Ooh, Sharwan, that is a very exciting emoji. My favorite emoji is the siren, because I like to use that when I tell people things that I think are super important. They're usually not. It's usually like many sirens, something exciting. All right, so our next question is about density. So a student in my research lab needs to utilize formaldehyde in their experiment. The formaldehyde we have is a liquid with density of 0.982 grams per cubic centimeter. How many milliliters should they add to their flask if they need to use 75.281 grams? So in this case, we have a mass and we have a density. So density is equal to mass, in this case grams, divided by volume. And there's 2 things we need to remember. So we're being asked for how many mils, and so we want to remember that 1 cubic centimeter is equal to 1 milliliter, and so we can convert our density into milliliters. So we have the 75.281 grams of formaldehyde that is needed. And now we need to use the density. So the density in this case is 0.982 grams per cubic centimeter. And we are going to be able to convert that to milliliters as a 1-to-1. So it also equals 0.982 grams per milliliter. Now we want to be able to use that to determine how many mils. So I'm going to invert or use the density as a unit conversion and divide by the density of 0.982 grams in 1 milliliter. And when you plug this into your calculator, you should get 76.7 milliliters of formaldehyde. What questions do you guys have about density in general or about how to do this? I really enjoyed looking at your emojis. I enjoy that Eric, I think that's a crab, and that's fantastic. And I need to figure out ways how to use that one more often in my texting life. If you have no questions, you can drop either the word none in the chat box, or you can drop some random numbers, something so that I know that you have no questions. Kirsten says she has none. And so does Catherine. Fantastic. And Patrick also has none. All right. So our next question reads, when 50 grams of a 0.2 molar sodium chloride solution at 24.1 is added to 100 grams of 0.1 molar silver nitrate also at 24.1 degrees Celsius in a calorimeter, the temperature increases to 25.2 degrees Celsius as silver chloride forms. Assuming the specific heat of the solution in the products is 4.184 joules per gram Celsius, calculate the amount of heat in joules produced. It also asks, what is the delta H reaction in kilojoules per mole of silver chloride? So, in this case, it never says that it's in a calorimeter, but it asks for heat, so heat equals Q. And Q reaction equals negative MC sub S delta T. So from here, we can then go on to look at different calculations to figure out how much heat in joules is produced. So in that case, we need to figure out the answers to our different values. So we have M, C sub S, and delta T. Delta T is T final minus T initial, so we are going to subtract 25.2 minus 24.1, and that gives us 1.1 degrees Celsius. The specific heat capacity comes just out of the question, and that is 4.184 joules per gram Celsius. And so the last part is the mass. And so the hardest or the most complicated part is that it is the total mass. And so in that case, it's going to be 50 grams plus 100 grams. And that gives you 150.0 grams. From here, we can just plug in these values into this equation to where Q equals negative 150.0 times C sub S, which is 4.184 joules per Kelvin. I forgot my grams here. And delta T is 1.1 Kelvin. So don't forget, delta T is Celsius and Kelvin are the same. So Q equals negative 690.36 joules. But based on our Sig Figs, we can only have two significant figures, which gives us negative 690 joules as our heat. So before we go on to the second part of this calculation, what questions do you guys have about this calculation in general? And if you have none, you can go ahead and write that right in the chat. And we will move on to taking the Q value to convert to the delta heat of reaction in kilojoules per mole of silver chloride. Ooh, so Avery asks, how did you know that it was Q reaction and not regular Q? Because there is a reaction happening. So if we had wanted to, and part of the next step is to do that, to write that NaCl plus silver nitrate gives us sodium nitrate. I'm going to run out of space, and silver chloride. And so that makes it a reaction. Ooh, so Kirsten asks, why don't we add 273.15 to make it Kelvin? It's a good question. So if you added, so I'm going to slide this over to answer Kirsten's question. Ooh, and Catherine. I think that's what Catherine's asking. So we're looking for delta T in this case. And so we have two different heat values. And so delta T is what I gave you previously, is right here, of 1.1. So the alternative would have been 25.2 plus 273.15 minus 24.1 plus 273.15. And that would have eventually given you 1.1 degrees Celsius or 1.1 Kelvin. And so delta T, you can subtract the Celsius values or the Kelvin values, but the change in temperature will be the same because you increase them both by the same amount. So whether you measure it here or up here, it will give you the same delta value, but you can't leave it in Celsius for anything in chapter 10. And that's where the confusion comes from. Great question. Oh, and Mahi answered that in the chat. So good job. So Bertram asks, is it a different question if it was regular Q? Yes. So a regular heat reaction is Q equals M C sub S delta T. So not both of those. So it's either Q equals M C sub S delta T or Q reaction equals M negative M C sub S delta T. Get all my things in the right place. There we go. So the second part of this question asks us something different. It says, what is delta H reaction in kilojoules per mole? So in order to do this, we need to remember that Q equals delta H. And so one thing that students often want to do is they just want to say like, oh, Q equals delta H. But it does. But in this case, it asks us in kilojoules per mole silver chloride. So one thing students like to do is to take their joules, convert to kilojoules, and then swap, like just plop a per mole. In this case, we need to take, in order to determine delta H in kilojoules per mole, we're going to take our Q and divide by the moles of silver chloride. And so we need to figure out how many moles of silver chloride we have. So in this equation, in this question that I probably would have given to you in a different way, so it tells you that you have 50 grams of 50 grams of one solution and 100 grams of another. So in this case, I'm going to make this a little bigger so we can write above it, and then we'll move back down to the bottom. So 50 grams, the density of water, or of this, is 1 gram per mil. So in this case, it'd be 1 gram per 1 mil, and that gives you 50 mils. And so then we can multiply that and divide that by 1,000, 1 liter, and multiply by the molarity. And that gives you 0.01 moles of NaCl. Holy moly. Sorry. No one needed to see. That's the dog. Sorry about that. My iPad and I are having a fight today. So in this case that you cannot see because I wrote it under my face. So it's making an assumption, number one. Number two, I stole this question from the internet and then gave it to you and then kind of looked at it a little bit more later today. I would ask this in a much clearer way. So in order to do this, you would need to convert the value, whether it's grams or moles, into moles, and then you're going to divide. So we can take our 100 grams of the silver nitrate. We're going to convert that in 1 gram and 1 mil. And so that's going to give you 100 mils. When you convert that to liters, we can now multiply that by, we're going to divide by 1,000 and multiply 0.1. And this gives you 0.01 moles of AgNO3. That didn't need parentheses at all. All of this is to tell you that those were in equivalent amounts. So we can use either one and convert that into product. So I'm going to take my 0.01 moles of NaCl and multiply that by 1 mole of NaCl to 1 mole of AgCl. So the product amount is 0.01 moles of AgCl. So now we can take our Q value and divide by the moles of silver chloride. So we're going to take our negative 690 joules. We're going to divide that by 0.01 moles. We're also going to go ahead and convert that into kilojoules because that's what it's asked for. And so there are 1,000 joules and 1 kilojoule. And that gives you negative 69 kilojoules based on this. So I'm going to go ahead and make this a little bit smaller so you guys can look at it. And I don't want to say take pictures of your screen if you want to, but you could definitely do that. So what questions do you guys have about this calculation? 2 things to remember as you think about that. 1, the way this was written, it required you to assume that the density of both of these solutions was 1 gram per mil. I will not ask it in this way because I felt that that was unclear. And if they were not the same, you would have had to use limiting reactants to figure out which one controls the amount of product. Any questions? If you have no questions, you can drop a none, an emoji, and or a number in the chat box, and we will move on to our last question. Correction. We will move on to our last prepared question. I will answer any questions from the floor or the chat box as we move along. Thanks, Jeremy. So Hayden asked, where did the 0.01 moles of sodium chloride came from? So that came from this calculation up here at the top where we took the amount of sodium chloride and converted that into moles of sodium chloride. And then I used this value down here for space savings. And so that's where that value came from. Great question. Sweet. It looks like I'm not seeing any other questions, so we will move on to the second or to the last prepared question. So we have 4 examples, and those look quite tiny. So we're going to draw the Lewis dot and Vesper structure, and we're going to include the names of the electron domain and molecular geometry. So we're going to just start with PCl5 and then kind of move forward. So for PCl5, The first thing we want to do is calculate the valence electrons, which is 5 plus 7 times 5, which gives us 40. So per the directions on how to draw a structure, we're going to put our phosphorus in the center. We're going to connect all of our fluorines. Then we're going to add dots, and I'm going to try to lean back so that you cannot hear the tapping sound. So we're going to do our best. So once you add and create octet on all of your fluorines, so we have now want to ask ourselves, do we have any lone pairs left over? So phosphorus and fluorine to create all of this uses 40 electrons. So there are no lone pairs to put on the phosphorus in the center. From here, we can then start to draw a Vesper structure. So phosphorus is in the center connected to 5 things. That gives us a steric number of 5. And a steric number of 5 is a trigonal bipyramidal. So we have our phosphorus in the center, and we get these Of course I did. I don't really know where the fluorines came from. I just got excited, I guess. As Alexandria and Catherine have both pointed out, I don't know where the fluorines came from. And we're just going to pretend like I didn't draw those. So I've erased them. If you're just tuning in now, I drew fluorines instead of chlorines. And that's not the correct answer. So now back to my steric number of 5. We have our phosphorus, which is in the center. And so there are chlorines, not fluorines, on each of these. And so for a Vesper structure, you need to include all of your lone pairs. And once we draw this, it asks us to name the electron domain and the molecular geometry, and the other word for that is shape. And so both of these are trigonal bipyramid. So someone asked in an email, how do you determine molecular polarity? So the phosphorus chlorine bond is borderline polar. And so if you have something that is trigonal bipyramidal and you want to think about polarity, so in that case, you would look at the arrangement of all of these bonds. Because they're all the same, whether it is a polar bond or a nonpolar bond, this would be a nonpolar molecule. So the polarity is determined by the magnitude of the dipole moments. So because this doesn't have any one of these out of order, this is a nonpolar molecule. So that arose from a question that someone sent me via email, which is why it is not part of this. And I will ask specifically about polarity if I would like you to include that. So next, we are going to draw BrO2 minus, and I'm just going to roll the screen up because I cannot draw small enough to make any more fit on this page. So we're going to look at BrO2. Nope, this was O2 plus. So we have 7 plus 6 times 2. So, Abby, I'm going to answer your question after. We'll take a break after this structure and we'll look at bond polarity again. So it's 6 plus 6 times 2. So we've got a lot of polar questions. So the dipole moments for phosphorus, chlorine would all look like this. And because they're all the same, so if the phosphorus chlorine bonds are polar, all of them will pull the same. And so because they all pull the same, so the best way I can think about it is if two things pull on the top and the bottom at the same, the center mark here isn't going to move because they're the same. Bond polarity is about pulling unequally. And so I don't have a model kit at home, but I happen to have like 900 markers. So if we flip the molecule on its side, this is like not looking as awesome as I had hoped in my mind. Sorry. Nope. There we go. Give or take. This. Why am I making a structure? I can just draw this. If we flip the molecule to where the axial, if we move these two and we change the orientation to where what we see is the phosphorus and the three chlorines in the plane of the board, and so you would have the other two like this. So all I did was take the previous molecule and rotate it flat so we could look at those. These dipole moments, none of those can pull any greater either. And so in this case, the overall is nonpolar, even though all of the bonds are polar. The formal charge for all of these are 0. So for phosphorus, it would be 5 minus half of 10, which is 0. And chlorine, because they all look the same, we can do it once, is 7 minus half of 2 minus 6, and that is also equal to 0. Great questions. So now we will move back to BrO2 plus. So we have 7 plus 2 times 6 minus 1. So we're going to subtract 1 due to the positive charge, and so that gives us 18 valence electrons. So here we are going to put all of our lone pairs around. So here we've used 2, 4, 6, 8, 10, 12, 14, 16. And there's 2 left here. So then we're going to make a double bond, which gives you Br double bond 0, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Oops, we have a lone pair here. So we're going to go ahead and make sure that the formal charges, so we'll call this one A and B. For OA, it is 6 minus half of 4 minus 4, which is 0. For OB, it gives us 6 minus half of 2 minus 6, which gives us negative 1. For the bromine, we have 7 minus half of 6 minus 2. So 7 minus 3 minus 2 equals plus 2. So we have a 2 plus here and a minus here, which gives you an overall positive charge. And so in this case, we now have a Lewis dot structure with formal charges. And so we can ask ourselves, what is the Vesper structure? So connected to the bromine, there are 3 things connected. And so that gives us trigonal planar. So we have something that looks like this. And so it doesn't really matter where you put anything else. So we have a lone pair here, a 2+ here. And then we have an oxygen with a double bond and no formal charge, an oxygen with 6 electrons and a negative bond. If it asks you for a resonance structure, in this case, the question wasn't, it didn't say you should have one or not, but in that case, there is a resonance structure that would look like this. Where we have a negative charge and still a 2+. So these are the two structures. So for the bromine, oxygen is this polar, and based on the electronegativity of bromine, which is actually very close to oxygen, because as the trend decreases as you go down, and it turns out those two are at closer values then, and so they fall into a nonpolar bond. So this would be a nonpolar molecule. Nonpolar based on the bonds in this structure. Any questions about BrO2+? Not seeing any questions just yet. Give you guys another second, and then we will look at COH2. So for our next one, we have CO. Yeah. So Catherine asks, can you define polar and nonpolar? Sure thing. So if you remember electronegativity, so electronegativity is basically the question of how much an element would like to bring on an electron. And so the periodic trend for that is that it increases as you go across and it decreases as you go down. And so if you want to know if a bond is polar or nonpolar, so a nonpolar bond is defined as so all of these are chi1 minus chi2, where chi is the electronegativity. And so nonpolar is 0 to 0.5, and a polar bond is 0.5 up to 2.9, and an ionic bond is anything greater than that. Otherwise known as a metal plus a nonmetal. So when the trend for the bromine-oxygen bond, so if oxygen is here and it is here, the further apart they get, the less. So bromine is substantially less electronegative than chlorine and fluorine. And so the difference between those two tells you whether or not it is nonpolar or polar. And so without looking, that is far enough apart that they should be nonpolar based on the electronegativities. And so the other part of that definition is that nonpolar, these share electrons, and a polar bond, that looks like shaves. And I would say that a polar bond hoards electrons. So they have an unequal sharing event. So Bertram asks how did you do the equations again? And we'll slide back over here. And we're going to erase this. So this is the valence electrons minus half of the bonding electrons. So that's the number of electrons in a bond minus the lone pair electrons. So if you, on the homework system on ALEX, it calls it so they do a slightly different calculation where their calculation is the valence electrons minus the number, weird way to draw that, the number of bonds minus the lone pair electrons. And so I got those numbers. So if you look at this structure up here for bromine, bromine itself has 7 valence electrons. That comes directly out of the periodic table. And there are 6 electrons in bonds in and around bromine. And so you get those by counting up these two and this one. So each bond has 2 electrons. So that's a total of 6. And then there are 2 lone pair electrons. And so those are the electrons that you see here and here. And when you add those up, that gives you a +2 charge on the bromine itself, as opposed to one of the other structures. It's a good question. So let's come back. If you have other questions, you can drop those right in the chat. We have COH2. So the valence electrons are 4 plus 6 plus 2 times 1. And so that gives us 12. So the first step for a Lewis dot structure is to put carbon in the middle and connect an oxygen and a hydrogen and a hydrogen. So hydrogen now has the complete octet. And so we can complete the octet for oxygen. So we've now used 2, 4, 6, 8, 10, 12. All of our electrons. So the thing is, in some places, this is great. But carbon doesn't have octet, and carbon isn't allowed to not have octet. So there are some elements such as aluminum and boron and gallium that can, but carbon isn't one of those. And so in this case, we need to give it octet. And we can do that by taking one of these lone pairs and creating a double bond. And so that would give us C double bond O, hydrogen, hydrogen. And so we can check the formal charges. So the formal charge of oxygen is 6 minus half of 4 minus 4, which is 0. For carbon is 4 minus half of 8, which is 0. For hydrogen, it is 1 minus half of 2, which is also 0. So there are no formal charges in this molecule. From here, we need to draw a structure. So there are 3 things connected to the carbon, and that makes it a steric number of 3. And so when we draw that, we're going to put our carbon in the center, and using bond angles of approximately 120 degrees, we get a trigonal planar. So the electron domain and the molecular geometry are both trigonal planar. So what questions do we have about the structure of COH2? And so the central atom was underlined on the left. I'm not seeing any questions, so we are going to look at the arsenic hydroxide. So I wrote this question the other day, and as I was making the key for myself, I realized that this was kind of beyond the scope of what we had talked about this semester. So I will draw the right answer in a second, but for the purposes of this discussion, we are going to change that OH3 Ooh, some good questions are coming up first. So Bertram asks, when do you know when to? So the steric number of 3 can be all in the plane of the board. So you could have alternatively drawn this as this. With the 2 hydrogens, and that would have been there. And so the polarity, one second. So in this case, the bond polarities, so the carbon-hydrogen bonds are, so CH is nonpolar, and CO is polar, and the polar bond looks like this. So we have no polar bonds on the bottom, and so we have a single polar bond, which gives an overall, so the molecular polarity is in this direction, which makes it a polar molecule, based on the fact that CO is polar and CH is nonpolar. Good question. Sorry, I included that on the first one, then forgot. Kayla is right. Your best bet is to use the Vesper chart that shows you examples for all of the different ones. Any other questions about COH2? So the arsenic hydroxide, we're going to change that to arsenic. We'll just leave it alone. So in this case, this one is a little different because the arsenic is connected to 3 different hydroxides. And so in that case, we can start to think about what does that mean for valence electrons. So arsenic has 5. And each oxygen has 6 plus 1 for a hydrogen, and there's going to be 3 of those. So in that case, we have 21 plus 5, so that gives us 26. So based on the chemical formula, we can start to think about what this looks like. And so we're going to put our arsenic in the center. Then we're going to connect it to each of these hydroxides because they're inside of the parentheses. So we're going to have O. And then each of those are going to be connected to a hydrogen. And we know that because the chemical formula shows us that the OHs are stuck together. So from here, we are going to continue to add electrons to make octet. And so we can add 2 here, or 4 to each of these oxygens. And that's going to allow us to complete octet. So the hydrogens have octet, the oxygens have octet, and so now we need to look at, have we used all of our electrons, and is this enough? So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there's 26. That last 2 goes on to the arsenic. So all of these have octet. And so now we can look at our formal charges. So for the oxygens, the formal charge is 6 minus half of 4 minus 4. And that's no charge. For hydrogen, 2 minus half of 2 1 minus half of 2 equals 0. And for the arsenic molecule, it is 5 minus half of 6 minus 2, and that also equals 0. So none of these have a formal charge. So the question becomes, how do we take this big molecule and make a Vesper structure? So in this case, what we're going to do is we're going to put the arsenic in the center, and then we can work on the oxygens next. So arsenic has a steric number of 4. So we're going to put our arsenic here. And so now we can just add in our structures. And so we have a lone pair here. We have an oxygen and an oxygen and an oxygen. Each of these oxygens have a steric number of 4. So then we can go ahead and add that in. An oxygen here and 2 lone pairs. We have a lone pair, and then hydrogen. So over here, we have the same. That's not right. So it gets a little bit more chaotic, but what we can see is that the steric number of arsenic, which is the one that's important. So for arsenic, it is a tetrahedral trigonal pyramid for the electron geometry. And it's actually only asking about the arsenic. And so does this molecule have a... So the polarity of this molecule is quite complicated. So arsenic oxygen, let's move this over here so we can have a little bit more space. So the arsenic oxygen bond is polar in that direction. So the bond polarity of this is a little bit crazy. So it would pull in all of these directions, which gives you an overall bond or an overall molecular polarity. I think of this because all of the 3 oxygen bonds are pointed in that direction. This is an exceptionally difficult molecule for you to be able to determine the bond polarity or the molecular polarity of. I will not ask you one that is this hard on the midterm. Or no, whatever test we have this week. It will not be this complicated. It will be similar to the other examples. So what questions do you guys have based on this example? Do you have any other questions today? I'm happy to answer a few more if you have them. If you don't, I will see you all in class, or I have some Zoom office hours tomorrow. And if you have no questions, you can drop none right in that chat box, and you can go ahead and head out. And I've had a wonderful time. I hope you guys have had fun today too. So Alexandria asks, I see Eric's question about calculating heat and energy. We will answer that one after I answer about formal charges. So formal charge Nope, not formal. Okay, just gonna move that up and start over. So formal charge is equal to the formal charge is how many electrons does any given atom get to count towards itself. So it tells you whether it is a positive charge or a negative charge or no charge. So for any atom in a structure, it's the number of valence electrons, and it is going to be minus the electrons, or I always think of it as half the electrons in bonds, minus any lone pairs. So in this case, I'm going to draw the Lewis-Dot structure for water. So the question, the formal charge of oxygen in this molecule is asking, how many electrons does oxygen get to count towards itself? So oxygen only gets to count half of the bonds, all of its lone pairs. And so when we think about that, so oxygen has 6 valence electrons. So it has 6 valence electrons, and it's minus, it gets half of the bond. So each bond has 2 electrons. There are 4 electrons where there are 2 bonds, so half of 4. And then this oxygen has 4 lone pair electrons, so minus 4. So 6 minus half of 4, which is 2, minus 4, and that gives you 0. So the formal charge is a calculation to measure how much or how many electrons anyone gets to keep. It's a great question. So in the chat box, Bertram asks, because other people might be curious, are there any possible subjects that you haven't gone over during the review that will be on the final? Yes. There are other things that will be on the final. This is a broad review. I would suggest looking at your old mini exams for things that I've looked at, things that you feel like we did lots of examples in class. I tried to do as much as I could in this session without giving you a review of the whole course. So there are a few other topics, many other topics, that will be on the final that we did not talk about today. Alexandria, if you have more questions about formal charge, let me know. So let's look at Eric's question. So Eric's question in the chat box. Sorry. Is as follows. So we'll just put it right up there. So a system loses 916 kilojoules of energy while gaining 412 kilojoules of heat from the surroundings. What is the work done? So in this question, the equation we want to think about is that delta E, and I should not write in the middle of the question, sorry. Delta E equals Q plus W. And so in this case, it gives us 2 of the values, and we need to solve for the third. So a system loses, so delta E is equal to 916 kilojoules. And so we need to determine, is it negative or positive? So the system lost energy, so it is going to be negative. So, and then it says, while gaining 412 kilojoules of heat, from the surroundings. So Q is equal to 412 kilojoules. And because the system gained heat, so the heat went in, it's going to be positive. So in this case, we need to solve for work. So work equals delta E minus Q. And so we can plug in our values of negative 916 kilojoules minus positive 412 kilojoules. And that gives you negative 916 minus 412, and that gives you negative 1,328 kilojoules. Does that answer your question, Eric? Is this the type of example so that the more complicated parts are remembering that when a system gains or loses something, if it gains it, it is positive. If it loses it, it's negative. And so sometimes these calculations will write the heat is lost from the system or it's lost from the surroundings. So you want to make sure that you look at all those. Just check in through the chat, see if there's anything in there I'm missing. Perfect. I'm glad that helped. So the other question, so Skylar says for rhodium 3 plus, sorry, how do you write that configuration? And so you write rhodium 3 plus by following the same exceptions. And so in this case, so I wrote 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this part, 3d10, 4p6, 4d6. You do not need to include the 5s0. You can. You could have added right here a 5s0, but by it being missing, it is missing. So you don't need to include it. You can include it if you need to. Skylar, does that answer your question? So the other question in the chat box is from Nikolai, and he asks if we could go over a titration question. But when you do the example, just do it in terms of numbers. So you're so welcome, Skylar. A titration is a measure of when the moles of acid and moles of base come to equivalence. And so in order to do that, you want to be able to, so there are a couple of key steps. So the first step is you need a balanced equation. And so once you have that, you need to, so in part 2, you want to determine moles of known. And you can either do that, and the example I did way at the beginning, I think it was the very first one, which you can rewatch earlier, and I'll flip back to that in just a second. We did that from grams to moles. If you have a molarity question where it has 2 concentrations, you could use the molarity times the volume. But you need to determine the moles of known. So this uses grams and molecular weight, or the volume and molarity. So then we are going to convert moles of known to unknown. And you're going to use the balanced equation. So once you have that, then we can go in and determine the concentration, which is usually what it asks for. And we can determine molarity, which is the moles of unknown divided by the volume of unknown. So in this case, this is how you would set that up from a broad perspective. And so in this example, you want to make sure, or in this topic, you want to make sure that you're not using M1V1 equals M2V2. So we looked at an example for that early on. Make sure all of this is in view. And so in this example, we have a titration where we first developed an equation, which is 1 mole of oxalic acid plus 2 moles of sodium hydroxide gives you 2 moles of water plus 1 mole of sodium oxalate. Then we used the 1.28 grams of oxalate and converted that to moles. So this, back in the graphics that we showed earlier, this is step 2. From there, we used the balanced chemical equation for step 3 here, where we took the moles of H2C2O4 and then converted that to sodium hydroxide using the balanced chemical equation. Then in step 4, we divided by the volume, and then we're able to determine the molarity with the correct number of Sig Figs. So this is how you set up a titration question. Anyone else have any other questions? If you do, you can go ahead and drop it in the chat. Otherwise, let me know that you are headed out, and good luck studying, and I will see you guys either tomorrow or Wednesday, depending on when your final is. I will stick around for another minute, but I am starting to get hungry, so I need to go just here in a second. This video will be stored on my channel as soon as we hit finish. Well, it will take about 5 minutes for that to happen, but otherwise, you can rewatch this at your leisure. Any other questions? If you have them, drop it in the chat. Otherwise, I will see you guys later. Nikolai, do you have a specific example of the ionization series that you're thinking about? I mean, you can go ahead because these are all the questions that I have prepared. So you can do that, or you can stop in tomorrow during office hours and we can go over ionization series together at that time. So the question Nikolai has is which of the following elements, and those elements are potassium, magnesium, aluminum, and phosphorus, does this ionization series belong to? So ionization is the ability to create plus ions. So we're going to go from X to X minus plus 1E. Nope, X plus, sorry. So we are going to remove electrons sequentially. And so when you do that, at some point you break the noble gas core. So we're looking for the large gap between them. So if you look at I1 to I2, this gap is somewhere on the order of 1200. This gap is 32,569 minus 1816, and that gives you 30,000. And so as you look at this is approximately 4,000, and this one is approximately 5,000, give or take. And so they can be approximate because that's acceptable. So we know that this gap right here between I2 and I3 is the destruction of the noble gas core. So this is the big jump. And that destroys the core. And so the question we have to answer is, which of these, when they go from X2 plus to X3 plus 1E minus, is destroying the noble gas core? So in that case, you would look at each of these ions and look at their electron configuration. And so in this case, the answer that I get is magnesium. So I get magnesium. Whoops. Because Mg, so I1 is Mg goes to Mg plus E minus. So I2 is Mg plus goes to Mg 2 plus E minus. And I3 is Mg 2 plus to Mg 3 plus E minus. And if you look at the electron configuration, the magnesium 3 plus destroys the noble gas core. So this destroys the core. Great question. Any other quick questions? Otherwise, I am going to go ahead and go so that you guys can continue studying. Feel free to email me. I will try to respond to emails at least once this evening if you have any other burning questions. Otherwise, I have office hours tomorrow. You can look in the announcement to tell you what time they are. And as I think Eric asked, I will post the keys for the midterm exam here as soon as I hit finish. I'm not seeing any other questions in the chat box. You guys have a fantastic evening, and I look forward to seeing you guys at your final.